We'll now listen to Javier del Hoyo on new methods to identify the origin of inflow woods. So we'll be able to go into more details and possibly finalize the discussion on the issue of origin of wood. Javier, you have the floor.
Thank you very much. So, can you hear me well? Perfect. Well, thank you everyone for joining today. My name is Javier del Hoyo. I'm a PhD candidate working with Virginia and also collaborating with Hervé and other people. And we are studying right now new methods to detect the origin of Instream wood. First of all, sorry, I'm going to change this just in case. So first of all, why do we need a method to infer wood origin? Well, just to illustrate, if we take this example, this is like a basin with a dam, kind of similar of what we have. The vegetation, it's providing some wood to the river that eventually, after some flood events, could finish just retained by the dam. So once we have the wood here, how can we know from where it came? Maybe it came from this area or from this one, but more from the upper side or the lower part. And this is actually essential. What we have to do is to go to the wood that we have here and try to find the clues that are going to tell us from where it came. So to find these clues, we go to dendrochronology. That is a scientific discipline that assumes that the pieces of wood are archives that are storing data related with a lot of different things like climatic conditions, past climatic conditions, but also geological information or events that happened in the past, like landslides, floods, fires, and so on. This dendrochronology discipline has a lot of different subdisciplines that you can apply. And we focus on the dendroprovenance that uses this data stored in the wood to infer the provenance. This is used in a lot of different fields, like archaeology, to avoid commercialization of pieces of wood that comes from protected areas. Also to infer the origin of oceanic wood. And of course, to know the origin of in-stream wood. That is the one that we want to talk today. Dendroprovenance techniques are diverse, mainly these 5 you see here. So, of course, taxonomical identification. Using mainly a microscope, you can see the anatomical structures and infer or identify your sample, which is very important. You can also use cross-dating chronology, so comparing the tree rim width, you can see some similarities, although this is not very useful in riparian vegetation, but could be used with other kind of vegetation. The chemical composition of the tree is also very useful, since 99% of the tree is composed by carbon, hydrogen, or oxygen. The other 1% is very diverse and is telling you holds a lot of information about geology, but also land use and so on. And this can be used to distinguish different areas. And actually, this is the one that we use. And finally, we can use also this table isotope radius that I don't know how familiar are you with this concept, but just briefly, so you know, an isotope, if you take, for example, the typical water molecule, everyone knows, 2 atoms of hydrogen and 1 of oxygen. Well, sometimes it's not always the same. And sometimes the atom, for example, if we look here, the atom of oxygen used to have 16 neutrons and protons, the same, but sometimes could have some extra neutrons. So only the mass is changing, but the other characteristics of the atom and how they relate with others and create molecules is the same one. So it's going to have some physical differences that we could use to as a tracer to for example, in this case, to infer the origin of this wood. So far in the Genesiad, we have used these tracing techniques to fingerprint the wood. In the past, it's used, of course, taxonomical identification, since once we go to the Genesiad dam and there's some extraction, we go to the pile and we cannot know exactly which genera or species are there. So we have to go to the microscope and identify them. Then the chemical composition had been analyzed in the past by Audrey in this master thesis Hervé was talking about. He supervised, also co-supervised by Virginia, where they determined the origin of the wood. And also Hervé with other people were working in something similar in the Isère River to analyze the chemical composition of the wood. They used XRF in this master thesis I told you, and this wasn't like very promising. They were using like directly the pieces of wood, using like this X-ray through different angles on the piece of wood, but it wasn't very good. Although it was the mass spectrometer method, where, as you see here, focusing on like significant elements with using this factorial element discriminant analysis. So calcium, iron, or silicon that is just below this one could be used to distinguish different areas so were relevant elements. And here they could distinguish between like valserine, basin, or the area, the upper part of the earth, like the Chamonix. So this was very useful, but still we wanted to add some information. So not only related with the geology, since sometimes different areas very far from each other could present similarities in terms of geology. So we wanted to add to this chemical composition method to add another one not related with geology. And that's why right now we are using this new method based on this stable isotope, and specifically in these two, so hydrogen and oxygen, that are related with the water molecule. We are using the mass spectrometer to do this, and now I'm going to explain you just briefly so you understand why we are using the water molecule and the stable isotopes within it. Just so you know what you do with the stable isotope radius, like you infer this radius, dividing the less common isotope by the most common one. So, and then you standardize using a reference sample. In the case of the water, what we use is the ocean water as the reference. What it means that if you take a sample from the ocean, the value could be 1 minus 1 could be 0 per mil. That is how you express this kind of radius. So now you can see why in the ocean now we start with a 0 delta value. And then let's say like this water evaporates. When it evaporates, like the lighter isotopes tend to evaporate and the heavier remain, like preferentially. So that's why this cloud is lighter in isotopic terms. Then when it precipitates, the heavier isotopes condense preferentially, and that's why this rain is heavier. And then a second precipitation could be lighter since less heavy isotopes remain. All this water, they're creating different streams and they have their specific isotopic signal. And these molecules are going to be absorbed by the trees when they take up the water with the nutrients, and they are going to store this information, this isotopic signal in their rings. So this is what we are using right now as a clue to infer the origin of the wood. If we go right now to Genesiad Dam, so this is the area that we all very well know. And of course, as we were discussing, and similar to what I told you before, this vegetation, of course, is providing some wood. Eventually, this wood finishes in Genesiad. So how can we know the origin? What we are doing is we select some points, some areas in the in both basins. We collect some reference samples from living trees, and then we go to initiate. When there is extraction, we go there, we go to this file, we collect different, like a lot of samples of wood. And then what we do is try to match these samples with the reference samples that we have and say like, okay, this one comes from this area, this one comes from this one, the other one from this one. And this is the idea, to match known reference samples with the unknown one. So far, like I just started, I'm starting my second year. So I have been working in the upper and the lower part of both basins, collecting reference samples. And I'm going to show you just briefly. So I've seen some significant differences doing some statistical analysis in wood that is from the upper part of the earth. If I look on the hydrogen, so sorry, I didn't explain, but the left, we have like the results that belong to the hydrogen analysis, while in the right, I have the results of the analysis for oxygen isotopes. So if we look on hydrogen, we could see significant differences of the wood from the upper part of the earth compared with the others. And also, if we look on oxygen, we'll see differences, significant differences. The wood is from the area of the down valsarine and up valsarine. So we are also able to distinguish between these two areas, the upper and the lower part of the valsarine. And this other graph, it shows you how one variable is related to the other ones. So oxygen and hydrogen, how they relate each other. And in red, you see the earth, so the upper and the lower part of the earth, and in green, the valsarine upper and lower part. And as you see, like the valsarine is gathering kind of in the center, while the earth has like a more dispersion or distribution, the dispersed distribution in the graph. And we need to do more analysis to see why this is happening, but also like these two areas could be related also with the method we followed. We're trying to find new methods, and we'll keep working on this. So just so you know, and now I will expect to answer some of the questions we were discussing before. In the short term, my future plans for this project is to do more samples per point. So the scientific statements will be more robust, and the results we have. We want to combine this, as I told you, with the chemical composition, these macro and micronutrients. And for this purpose, we are going to try to use the XRF. That is a cheaper method than the mass spectrometer, but with a new method. So as I told you before, in the master thesis, Adri used like this XRF directly over the pieces of wood in different angles. And this could not be really like useful because of the characteristic of the wood material, since this is porous. So this new idea is like to take the piece of wood, this is a core, we get powder of it, then we mix it with wax, so we have like an homogeneous sample, and then we put it in the XRF. And this is kind of what they use in sedimentology, for example, and we expect to have better results with this new method. And in the long term, in my project, I will characterize the riparian vegetation of both basins, the earth and the valsarine. And I will focus on the composition. So as Virginia said, like not only the species that are composing the forest, but also like the distribution, density, the presence or non-presence of invasive species, the age, and so on. And also, of course, the phytosanitary status that is like a main factor on this. And of course, we will focus on the different types of kind of management that is taking place in the different areas of the basin, so in different extents of forest extents. And we will also analyze the relationships between the amount of food that arrives at the Genesiat and the flood events that are supplying this food, having like keeping in mind all of these concepts that I told you before. Just to finish, so how can we use all of this knowledge, this research, to put it in practice? So if we better understand and if we have some method to infer wood origin, and we also understand better like why certain areas are contributing more or providing more in-stream wood than others, we will have some scientific tools for decision making in terms of the management of the riparian forest. We will also better manage the in-stream wood budgets, so the input of wood into the fluvial ecosystem, and thus the wood that arrives at Genesia Dam or any other dam if we apply it to another area. So ultimately, what we have is like a way to get to a better balance, to better way to find a balance between the ecological benefits that the in-stream wood, the presence of in-stream wood has in the fluvial, in the river, and also keeping in mind the fact that we have a lot of different infrastructures all along the rivers, not only dams, of course, but also bridges and population standing close to them. And to get a good balance in this is essential for the present and also for the future. So thank you very much for your attention. And now I'm at your disposal for any question you want. Thank you.
If I will understand, first, in the slide 17, you show the...
Sorry, I can go back. Yep.
Yes. Yeah, actually, as I asked you, here we can see, for example, top right, yeah, there we have no top right. We have downstream of Arv and upstream of Valzorin, which have the same traces. So how can you distinguish between these two? And also we have a region, for example, from 27, we can say to 20, I don't know, to 30, that we have a bound of superposition. So if in one sample at the Genesia, you find this trace, how can you contribute and how can you say if it comes from where?
Well, first of all, like we don't have like the definitive like way, like method, like we need more samples to be more robust. So right now with what we have, for example, the main difference here, it's only in the mean, as you said, like the here, like the, or all of them are distributed in the same area. Even like if we compare up Valserine and down Arv, they present a different distribution in this area, but still like the idea is not only to look 1 year, because the main thing is that here I'm gathering all of the results in the same place. But I didn't put this, but I can show you like another, wait a moment, another graph. If I go here, for example, yeah. So it's important for us not only to look to all of the data, but also like in a temporal scale. So it could not be as easy, like for example, in the other graph I was showing, if you see like, if you go back since 2015, all the data, it's more like gathered in the same area and then they start to spread. So this is why, for example, we will try to use these 5 last years where the data is more spread. So it's not only like to take a sample and be sure that it matches to this area, but try to find like the proper years, for example, that we could use for this isotopic signal. And of course, to combine this with the geology that I said before, because only with the isotopes, it's not enough, since if we only use, for example, we were not talking about riparian vegetation, but I don't know, like more vegetation more subjected by climatical and non-local factors, could be easier, but the river is like, there's like a smooth in the isotopic signal. So it's not as easy to use only the isotopic signal for this purpose. That's why we need to combine both methods. So it's not only to see significant differences in all the data from the down Earth, but also like in a temporal scale, it's important for us.
Okay. But at least you can say, for example, it's 50% comes from upper Earth, it's 30% from this station, and I don't know, for example, 20%. So you can finally give us at least a percentage of the probability it comes from where, yeah?
Mm-hmm. Yeah.
Okay, very good, very interesting.
Thank you.
Thank you. I think you can.